Hi, I'm Dave Rees. Welcome to our home, which is also the home of Highline Electric Motors. Today I'm going to talk about my favorite subject, which is building and flying small electric models. I'm going to start by defining just what we mean by small electric motors so you can understand what we're talking about there. I'm going to discuss the advantages of the electric motors, and there are many. We'll go into descriptions of each of the motors so that you can see what size there is for each one and help you work with them. I want to discuss props, which are very important because they are different from any other type of power. We'll cover a lot of aspects of design to help you convert planes from other types of power and build ones from scratch. We'll discuss a good section on building and installing electric power in models, including soldering. One of the more frequently asked questions is batteries and charging, and we'll try and take the mystery out of that for you. The big fun part will be flying, and we have some great shots for you there, and we'll discuss trimming and adjusting them. I'll talk about where we are with RC with respect to this size airplane and what's ahead, what we can expect in the future. I'll end by discussing some of the more advanced projects which are very possible with electric power. And when you get more proficient, you'll be interested in those. The term small electric motors is a relative one, so let me try and clear that up by telling you exactly what I mean by small electric motors. Years ago, the founding fathers of the electric power industry hit upon a system of numbering electric motors which compared them to the only thing they had at the time, which was internal combustion engines. For instance, an 049 internal combustion engine became equal to an 05 electric motor, and an 02 internal combustion engine also became an 02 electric motor. So to put these motors in perspective, the largest one we make is equivalent to an 035 internal combustion engine by that system. And we go from there on down. In other words, our niche starts at 035 engine size. Nowadays, the power units are watts. It's a much more usable form of describing an electric power plant. Of course, watts equals volts times amps, if you remember your physics. And the largest motor, which was an 035, is equivalent to a 50-watt motor. So our largest motor is a 50-watt motor, and it goes on down through a range of sizes to a 4-watt motor. Now you get an idea of our niche in the market. Another way of describing our units is that they are not racing types. These are not extremely high performance. They're just normal performance. It has to do a lot with the magnets that you use. To get more power out of an electric motor, you need to increase the magnetism. And our motors all have ferrite magnets. Ferrite is a mixture of iron particles and various polymers which they mold into accurate magnets. The racing type motors use cobalt magnets and neodymium iron boron, a lot of high-tech magnetic materials, all of which make them more expensive. So ours is more of a cooking version than a racing version, if you will. Then to put it in really concrete terms, our motors will fly a plane about this size, which has our smallest 4-watt motor in it. It's about 16-inch span and about 60 square inches. This is one of our more or less entry-level airplanes. This is the one we include a plan with on the back of the instructions. When you buy this particular type motor, you automatically get that plan, whether you want it or not. And it makes a great entry-level model. This airplane here is probably an example of just about the largest size our motors will fly. It's a scale model, considerably more difficult than the entry level, but trying to give you an idea of the bulk factor here. It's about 220 square inches. It's a model of a German seaplane built between the wars for joyriding on Lake Constance in Switzerland. Wouldn't that have been fun to ride on back then? Our customers are fairly diverse. We have absolute beginners just starting out in the hobby. We get a lot of folks that flew rubber power. They seem intrigued with this. Even some indoor flyers. We also have the rubber scale class interested in this very much. There are classes in the FAC world for electric power, and it's a hotly contested field. Plus we get a lot of RC flyers, surprisingly, that are looking for smaller places to fly and more simple, less complex systems to work with. For nearly 60 years now, we've been flying models with internal combustion engines, and probably rubber power a lot longer than that. So we know those all pretty well. We have that all worked out. But electric is new. Electric power is the newest form of power on the map. So it's understandable that people will feel uncomfortable about it. So we're trying to overcome that with this tape. Let me describe some of the advantages that electric has for you. The most obvious ones are they're clean and quiet. It's very easy to wipe off electrons. It doesn't make any mess at all. The quietness is about like an electric drill in the sky, if you could imagine that. It's sometimes even quieter than rubber power is. One of the things I like is they're extremely repeatable. When I pick up an electric model to fly it, I know that it's going to fly exactly like it did the last time. There's not going to be any freezing in the lines. There's not going to be any climbing of the hook. The motor is not going to get tired. All the things that we've come to expect on other types of power just don't happen with electric. I get a perfect start every time I throw that switch, just like turning on a light. I get no difference at all. It's almost boring. It's so repeatable. I'm used to motors that would backfire and shoot the propeller off and things like that. You just don't get that with electric. I come from a flying scale background. Possibly you can tell that. But I'll tell you that there is no other power system which is as transparent as electric power. If you were to look at one of these models, you would have to look long and hard to be able to tell just exactly what is in there for a power plant, other than what the original airplane had. You know, there's obviously not a Volkswagen engine in there that size, but there's no cylinder heads, there's no tuned pipes, there's no CO2 filler tubes, there's nothing, which is, to a scale flyer, a godsend. This is a dream come true. I've done my best with this one to disguise things. The batteries are underneath the seat. the charging jack is underneath the gas cap, so that all you really have, if you look very closely, is a little tiny switch right underneath the pod there that you can use to start it up with. This makes a very, very scale power system. The scale flyers love it, and it's a booming event at the FAC meets. Notice something else too, that electric props tend to be exactly scale length. This is just about what the real one had, and this one you can see also has literally a teensy prop compared to the bulk of the airplane. We get used to rubber planes that have enormous propellers, but this will give you a very, very scale effect. Another feature which I enjoy is that you can use any type of paint you want. I can paint this with watercolor if I wish. I can paint with 3 different kinds of paint bases and not have to worry about whether the fuel will hurt it or whether it will come off with the rubber lube or whether it will stain. There's nothing to mark it. You never have to wipe it off. That's a serious advantage. The power curve of an electric model is just ideal for flying, particularly scale flying, in that it starts off extremely steeply and then has a long flat spot where the power is exactly the same, and then only at the very end does it start to droop off and then stop, so that what your plane will do is fly its pattern like there was some giant pendulum in there because of its consistency. And then the only thing you notice when it quits is that it's not climbing anymore. With an internal combustion engine, I always hated the burst at the end. The plane would do a tail stand right at the end with the resulting stalls and whatever was left for that. Rubber power begins with its maximum power right away, climbs vertically practically, and then goes down in a steady ramp to complete shutoff. But these fly very steady for the entire run. One of the things the judges always improve of is the takeoff capabilities. If you remember, the AMA rules call for a complete ROG for all power scale entries. First of all, you've got a short prop, no problem with takeoff. And they take off so realistically, people will cheer. It's amazing. It reminds me of a B-17 with a full load of bombs taking off from a great runway over in Europe somewhere. The plane will taxi and taxi and taxi and finally lift its tail, and then the plane takes off, you know, a ½ an inch at a time and gradually pulls up, and just as realistic as anything you've ever seen. What else? The electric power is probably the cheapest power form you can get today. Sounds unusual, but it is. Our most expensive motor, the biggest one we sell, is $26, and it goes down from there. You can say that they're cheap enough that you can commit the power system to the airplane, only changing it when you have a disastrous crack up and you're going to save the parts. But don't ever think of changing one motor to another airplane. Just buy another one. They're not that expensive. So this is a surprising thing to most people. Both CO2 power and internal combustion engines are more expensive. You can think of our smaller power systems as costing about as much as one box of rubber costs. I've laid out here on the table an example of our entire product line. All of our motors are made by Mabuchi of Japan. This is a company known for its quality worldwide. Almost all motor manufacturers use Mabuchi motors as their base product. They're impeccable in their quality control, and we can vouch for them irrefutably. They only, unfortunately, sell in very large quantities. You can't go to the Mabuchi store and buy a motor. Their quantities start at 5,000 pieces. So that's where we come in. We make the investment and then resell them retail. We adhere to the principle of large diameter wire. Every armature in one of these little motors has a winding of wire on it, and we believe that the wire should be as large as possible to thereby giving you the lowest resistance you can to current flow. This allows you to use to obtain maximum power and quite usable power from very few batteries. It's a low voltage system rather than a high pressure, high voltage system. Once again, the magnets are all ferrite, which automatically sets the power level at the normal level. All of our motors have carbon block brushes in them. Carbon block brushes are the best for wear and for high current carrying. Never use a motor that doesn't have carbon block brushes. You will be disappointed. Now let's take a look in detail at the smaller line of motors.
The smaller Highline motors are all based on a rectangular motor, which is the same as those used in small cameras. It is rated by Mabuchi at 6 watts maximum. From this motor, Highline offers 3 power units. The first of these is the Micro 4, which is a direct drive motor. A direct drive motor mounts the prop directly to the motor shaft. The advantages are that they are less expensive and lowest in weight. Since they are light, they can fly smaller models. Propellers must be small enough so that they won't overload the motor, causing it to overheat. Never use a propeller larger than recommended, or you could damage the motor. The next motor in Highline's smaller motor line is the Mini 6, to which a gearbox has been added. A gear drive motor is more expensive because Highline has to build the precision gear train, but it's worth it because of the larger propellers that can be used. The last motor in Highline's small motor line is the dual Mini 6, which has 2 motors geared to the same output shaft. Coupling a second motor to the geared output shaft makes yet another jump in prop size and system power. The dual Mini 6 will turn a 7-inch diameter by 5-inch pitch prop and pull an airplane as large as Highline's larger round motors will. All of Highline's square, geared motors have a freewheeling feature. Prop thrust pulls the shaft forward, engaging the drive gears. It disengages when the motor stops. All of Highline's direct drive motors, even the smallest, are furnished with a metal prop adapter. This is pressed into the motor shaft and gives you a tapped hole to allow the prop to be held on with a screw. This allows many types of props to be used, and it also moves the motor mass rearward like an extension shaft does. The small square motors with gear trains have a shock absorber to protect the train from bump damage. It's a small length of silicone tubing which absorbs an amazing amount of energy.
Well, that was a look at our smallest motors. Here's an example of an airplane using the Micro 4, the direct drive 4-watt motor, and that's what you could do with a motor like that. It's a model of a Grumman skyrocket from 1940, fitted out as a twin. This concludes the part on the smallest motors, most of which of these began life as motors for cameras. Every time you push that button, think of our Micro 4s. Let's take a look now at our larger size motors. These all began life as accessory motors in cars.
For larger free-flight models and small RC ships, Highline uses several sizes of round motors. The IMP 30 is a 30-watt direct drive unit. The Troll 35 is also direct drive and derives slightly more power because it can tolerate running on more cells. Both of these motors are about the same size and weight and have the same mounting dimensions. Highline's largest motor, the L50, is the same diameter as the IMP 30 and the Troll 35, but it is longer and heavier by about an ounce. This is Highline's most popular RC motor and is equivalent to the popular Speed 400 series motors from Graupner in 4.8 volt form. Recently, Highline has introduced a geared 50-watt motor called the Gnome 50. The motor is the same size as their L50, but has an integral 2.1-to-1 gearbox. Not only does this allow you to use much larger propellers, but the windings are smaller for those flyers who prefer using more batteries and higher voltages than the other Highline motors allow.
Okay, that's the detailed look at all our larger motors. We've taken the larger motors a step farther and we've installed them in a high-pressure ducted fan. This is one of our newer product lines, and this is an example of the kind of airplane that you would fly with that. This is a model of a Bell X5. It's a late 40s jet, sort of a copy from a earlier German prototype. It's now hanging in the Air Force Museum in Dayton, Ohio. I believe it was Neil Armstrong was the test pilot, or one of the test pilots, for this very airplane. You see it here in a full RC version with 2-channel RC and the red flame blaster. So let's take our next shots and look at the details of the ducted fans.
Here's Highline's Blue Flame Blaster and Red Flame Blaster ducted fan units. The Troll 35 is used in the Blue Flame Blaster, which is suited for light free-flight ducted fan models. The L50 is used in the Red Flame Blaster. This fan unit is adaptable to lightly built RC ducted fan models. The duct bore diameter for each of these units is 2.5 inches.
So now you have taken the tour of our complete product line of motors, which we're justifiably proud. We think we have a motor that will fit your every need in this size range. Sizing an airplane to a motor, or vice versa, is one of the hardest things with electrics. This probably discourages more folks and is the leading thing that keeps people from trying it, I believe. This model right here is my first electric. A bit tired and a bit worn, but I took a model that really didn't work well as a rubber ship and put an electric motor in it, took it off the wall and flew it, and it flew amazingly well. That is an acceptable way to get you into the sport very quickly. Take something that's hanging on the wall that doesn't work, stick a motor in it and give it a try. If you're flying rubber power, you have a lot more flexibility than you realize. If it's not flying right, there is all sorts of power changes you can make. You can double, triple the size of the motor or the length of the motor. You can play all kinds of games. This becomes very difficult with electric. You have to be very close to right, or you end up tearing the whole plane apart. Once you've got a power plant in there, it's a lot harder to fix than a rubber job where you just put different lengths of rubber into it. It is possible to go in and put an additional battery or a different set of batteries. If you need a little more duration, you can put larger cells, that sort of thing. But if you've made the wrong choice size-wise, there isn't much to do except buy a new motor, the next size larger, and try and work with it. I want to get you used to thinking wing area rather than wingspan. Wingspan is only part of the definition of what an airplane is like. Wingspan, someone will call me and say, I've got this airplane, it's got a 26-inch span. What motor do I need? But nobody mentions that the wing is only 2 inches wide, and really there isn't much area at all, and the airplane is really quite small. Here's an example of an airplane. It happens to be rubber powered, but there's not very much wing on there at all. If you were to choose this solely on wingspan, you would make a pretty bad mistake. So consider wing area. The wing area is what flies the airplane. This ties right into weight, of course, as it does with wing area, because if your airplane weighs too much, then the wing must fly faster to lift this heavier airplane. And if it gets heavier, it has to go faster, and so on, to the point where you reach a limit where there isn't enough power in the power plant to pull the plane fast enough for the wing to lift it. Unusual concept there. And what does it look like? Yep, it looks like my motors did the trick. That was what was wrong. It doesn't have enough power. But really what it was, you were either too small a wing or too much mass, too much weight. We've taken some of the guesswork out of it. In our newest catalog, we've revised it and put all the wing areas and weight ranges that we could on all these motors. So at least you know that when you get our motor, you know what size of airplane is most likely to fit. Of course, remember this, we do give a range. Had one surprised gentleman that told me that he had stayed within the 150 to 250 square inch range and the 15 ounce to 20 ounce range. But he didn't tell me that he had used the smallest wing area with the heaviest weight. So don't crisscross the sizes and weights. If you've got a small wing area, go with the lesser weight. He said it was a great taxier. Configuration is an important factor. I don't have any good example here, but you can imagine a Fokker triplane versus something as clean as one of these airplanes, there's going to be a difference in the power required to pull a large, draggy, heavy frontal area airplane. These racing types took extremely little power to pull them. So you'll want to consider configuration and drag as you're trying to decide on your motor. The performance of the system goes by rules of thumb, and I have lots of thumbs. We have thumbs for everything, but the basic one is the thrust of the motor should be no less than 1/4 of the weight of the airplane. If it gets less than that, you wouldn't be happy with the performance at all. If it's that 1/4, the plane will fly like a light plane or like a big bomber with a modest climb rate. If you can get the weight to thrust ratio less, like maybe 1/3, why, it's going to perform really nicely and briskly. As little as a half, if you get the weight to power ratio of 0.5, it may be too hot to use free flight. You may be into the radio control category because the plane will be just so hot that your trimming mistakes will destroy the airplane. We're all still learning about this, and we will be glad to talk to you when you're considering an airplane. So give us a call if you have a question that, an unusual configuration. I'm gathering data all the time from other modelers and other flyers, and we're beginning to get a good feel of what works and what doesn't work. So there, to summarize, it's weight, drag, configuration, and wing area are all what needs to be considered. It's a fairly complex little equation you have to do to make this work. As a parting shot, I would strongly urge you to start with an entry-level type model. This is not as easy as it looks, and spend $24, buy a little set of motor, and build a little tiny airplane and fly it around. That way you'll get experience beyond what anybody can tell you, so that the stuff is cheap enough. We feel you can, break into it better that way. Propellers are a very sensitive item for electric motors. So I've included this section because it's an area where you can actually do damage. And besides that, your previous knowledge is probably going to work against you, so that your natural tendencies can cause great harm. An electric motor and a rubber-powered ship are so different, because if you put more power on a rubber plane, it doesn't hurt the rubber. But what the electric motor tries to do is try and turn that prop anyway. Being it the willing servant that it is, it will just draw more current, whatever it takes, to turn that propeller. And the next thing you know, you may have cooked the motor. So, if you remember nothing else, here's the read my lips part. Don't put a large propeller on an electric motor to increase performance. Mambucci prints curves and performance data for each of their motors. Let's take a minute to look at one of these, and I think I can explain exactly what's happening when you put a larger propeller on an electric motor. Okay, here we go. This is the technical part. If any of you are adverse to technical things, avert your eyes now. What I have in front of you is a curve worked up for me by Don Schrull, one of the former owners of our company, and he has graciously given me all these curves so that we can see what's going on all on the same piece of paper. What we have is, at this margin of the paper, is the Micro 4 motor on 2 cells running free shaft, no propeller at all. Across the bottom of the graph I have torque measurements. In other words, as we cause the motor to do work by putting a propeller on it, it will start moving in this direction. What you try to do is get the motor, select the prop so that the motor will run at the peak of its power curve. This curve here is power, and this curve here is efficiency. You notice one peculiar thing is that they don't occur at the same place. You don't get the max power at the same place you get maximum efficiency. So, if I select my prop so that when it's running in static condition, the airplane is in your hand, it's not moving, that's when you get your maximum power. Then as it flies and it unloads in the air, it moves back this direction, and you go to the max of the efficiency curve. That makes your batteries last longer, everything becomes more better performance. So that's where you want your prop to run, in this vicinity, from the top of the power curve to the top of the efficiency curve. Now look what happens if I were an ex-rubber flyer and I tried to put a larger propeller on there, even a small amount larger. I'll go, say, from 15 gram centimeters to 20. First of all, the RPM goes down. Bigger prop, smaller RPM. That's easy to understand. The current goes up. That means your battery lasts less time. The efficiency goes down in a giant jump. Plus the power goes down also. There isn't anything going for you. Everything you do to move it in that direction is negative to performance. And there's one last little sleeper. This curve here, that's motor heating. It's going up exponentially while all these others are going in straight lines. So what you have is a tremendous jump in heating from 15 to 20. So everything about putting a larger prop on there is bad for the motor. This curve shows the exact same motor, only this time running with 3 NiCad cells. We've increased the voltage. Here again is the zero load point, and the torque increases going this direction. Compared to the other curve, notice how voltage has just spread all the curves out in that direction. Remember, the other ones were much shorter and tighter. They now go farther out. But they're all the same basic shape. So you would again try and pick the prop that will give you the maximum of the shaft power curve in static condition, and then in flying condition drop back to the maximum efficiency point. Everything's fine, except you notice now that since this curve has moved over, the heating begins to have effect faster than it did before. In other words, when you get down here to the static condition, which is our maximum shaft power point, look what has happened to the heating. The heating has probably gone up double what it was before. You may not want to run this situation very long on the ground. Start it and fly it very fast so that you drop back to this position where the heating is much less. One last curve. This one is again the exact same motor, the Micro 4, only this time operating on 4 cells, showing the effect of increased voltage yet over the last curve. Here we are again at the 0 point, no prop at all, and moving this direction as we put bigger and bigger propellers on. Notice some interesting things happen. Again, we've got quite a bit more power, and also the efficiency has increased. That comes with higher voltage. But as we try and pick a prop now that used to run from our maximum shaft power point to our maximum efficiency point, the heating has gone completely off the chart on the static point. It plain won't work that way. The only one that will be anywhere near reasonable in heating is the flying point. So the only answer to this situation is to use a smaller prop. Get yourself over this way more on the curve. Even though you're missing the max efficiency, drop it over to a point about here and bring your maximum power over to here, just so that that heating doesn't go ballistic on you. These are some of the reasons why you can use smaller props when you get 4 cells. So now, after looking at the curves, you can tell what's happening within the motor and why the large propeller is detrimental. The Delphin is a good example of an airplane which couldn't have been made rubber power. The configuration just wouldn't allow it. The propeller is very small and there's nowhere to hook the rubber. So that prop selection here allowed you to build an airplane that you might not have been able to do with another form of power. I can describe the failure mode from a too large prop so that you know what to look for, at least, because in your experimenting you may still reach that point. It used to be that the failure mode was the solder melted. So you would make one brilliant sky screaming climb and then everything would stop when the solder came apart. Now Mabuchi's gotten smarter and they spot weld the wires together. So they'll take a whole lot more heat before that occurs. But now what happens is the next weak link in the chain, which is the armature, begins to melt. The armature is made of a thermoplastic molding material with a copper sheath on which the brushes run. And as it starts to get hot, it will distort slightly. Then the motor begins to run lumpy and lose power in general. It's very hard to see it unless you have a practiced eye. I get used to doing it because I get to autopsy people's motors. But if you have about a 10 power eye loop, for instance, you can look at the armature and see ripples in it that shouldn't be there. And that's an instance that you have injured the motor from too large a prop. I encourage you to experiment with props because different airplanes fly better with different sizes, but you must not get carried away and make them larger, because that's the old way you were thinking when you were a rubber flyer, and you shouldn't do that any longer. In this section, I want to describe and discuss what designs are best for electric power. In an electric airplane, we have much the same situation that you have in a full-scale aircraft. You have a large mass in the nose, like you would with a internal combustion engine, and you have a battery, which is another large mass, which would be similar to a passenger or perhaps a fuel load. The designer is then faced with fairly large masses that you don't have in some of the other modeling types. So that in a way that's good, because you now can work with an airplane that's very close to real scale airplanes, and they in fact are the best. Airplanes with short noses and long wings, just the opposite of what you look for in free flight rubber and some of the endurance style airplanes. They work the best because the higher torque of the electric motors and all is not quite as twitchy with the shorter noses. So that type of airplane is ideal. Planes like World War I type airplanes, extremely short noses. World War II airplanes, light planes, and some other ones that you, I'm sure, can find. The basic structure should be stronger than a rubber ship, but not quite as strong as an internal combustion engine airplane. So as you design or consider another design, you should be thinking about the weight of the structure. Rubber scale stuff would be too weak. You need to beef that up. If you're used to making it a 16th square fuselage, make it out of 3/32 square. Just that little bit stiffer is what it takes. Rubber models can be converted, and anything can be made to fly electric. But consider a plane like this, which is an ideal rubber subject. And a lot of the endurance rubber models are not unlike this. They have long noses, fairly short wings, big fuselages. And what happens with an electric is that you begin to put your mass forward for the motor with this long moment arm from the center of gravity. And to offset it, to balance that mass, you take your batteries to do the compensating. And the battery ends up way back here somewhere. So that now we have a plane with a polar mass problem. You've got fairly heavy weights at long distances from the center of gravity. That's a system that is not well suited to recovery from upsets. If you're in gusty air or situations where the plane would have to recover, it can't do it as fast because everything is a long distance from the center of gravity. You would be far better with things closer in. If a short nose put the thing here and the battery only had to be here, you have a much better situation. Your landing gear needs to be very sturdy, much sturdier than you're used to building. I say somewhere around what an internal combustion engine needs for landing gear. I first started making landing gear that was way too weak. Probably that airplane there was an example of one. And every time it lands, the landing gear was broken. You're working with a lot more weight than you're used to, and where it seems to get you is on downwind landings. When the plane's going downwind at a pretty good clip and hits the ground, it'll drive the wheels back up through the wings sometimes. I've had to repair most of my rubber ships for that reason. So make your landing gear really tough and mount it well into the structure of the airplane. Reinforce your nose areas with sheet wood. This is a little more than you do for a rubber model. You need that extra stiffness to handle the extra weight up front. And your plywood firewalls are probably better than balsa. You need a good deal of strength to support that motor and keep it from vibrating and moving around on you. I mentioned moving the battery to offset the weight. I always make my batteries movable to a point. In other words, as I build the model up, I leave a little extra wire to the batteries so that they can be balanced, used to balance the airplane across the center of gravity. And then when I get what I want, I glue them in place. You don't want them fixed right from the start, because then you'll end up having to put ballast in. And ballast, you know, you've got enough weight already. Let's not add any more ballast if we don't have to. Electric motors produce a tremendous amount of torque. More torque than rubber models, probably up there with internal combustion engines. And of course it's to the left. And you will end up putting all kinds of shims and trying to move this thing afterwards. So it's much better to, right from the start, as you're designing the airplane, build in right thrust. I use 2 to 3 degrees, which seems exorbitant compared to what you're used to. Down thrust isn't as important as side thrust. And a lot of my airplanes have no down thrust, but 3 degrees of right thrust. There is so much torque that the airplane will begin to spin to the left from the torque. And your first tendency is to correct that with right rudder. Then you fly, and the plane has a fairly decent power pattern. The minute the power cuts, you begin a death dive to the right. And it makes this tremendous spiral in from very high, often destroying the airplane. So the only answer is right thrust. I know of no other way, because you're tied from spinning left to spinning right. Now let's take a trip down to our drafting department, and I'll show you a rubber plan that's underway and show you some of the things that we would do to make that an electric model. Plus I can show you some of the other model plans and show you where they're structurally beefed up and so forth. So let's take a walk down and visit that department. We are now located in the design engineering department, and the subject under construction right now is a T-28 Trojan. The airplane happens to be for rubber power, just because I needed a rubber power at this point, but I was very clever and designed it with the exact proportions which could also be used for an electric, thereby broadening its use. It has a 122 square inch wing, which makes it set just about perfect for our Mini 6 motor. Some of the things on the airplane that I would change from a rubber power to an electric are as follows. The motor will mount quite nicely on this nose because it happens to have a plywood firewall. The Mini 6 would screw right onto that from the back, and you'd have that all set. The nose is essentially foam, so you have plenty of structural strength there. All you would have to do would be, about at this point, mount your switch and jack plate assembly. That's done so that as you're launching the airplane, you're in a convenient location to switch it on. And the last thing would be a battery pack. I'll be telling you more about how to mount the batteries when we do the construction part. My usual method of drawing plans is to draw it first on a pencil drawing, which is like a rough sketch, then build the model, and then re-ink the model for eventual publication. That way I get all the errors that I might have made. Let's go over to the building department and talk a little bit about some of the considerations necessary to build an electric model. I will assume you've already built other models, either larger or smaller, so I'll concentrate on the part that is different for electrics. There are 3 parts to a system which must be mounted and connected. the motor, charge jack, and switch and batteries. The motor is mounted differently depending on size. The smallest can be simply glued in place with gap-filling CYA cement. Don't let it run into the motor. Allow for down and right thrust. I prefer to glue metal or plywood ears onto the motor, which can then be screwed to a firewall and adjusted for thrust with shims. The Mini 6 and Dual Mini 6 both have holes for number 256 machine or wood screws. Use these against a 1/32 or 1/16 plywood firewall. Wood screws have the advantage of not needing nuts. With larger motors, it is a good idea to leave extra wire, just enough to remove the motor fully for service or replacement. The extra weight won't really matter. Our larger motors can be mounted to a firewall using 2 or 3 mounting screws tapped into the motor front. Don't forget to slot for the air vents. While on the subject of cooling, if you are planning to use standard battery packs, the little motors won't need much cooling. Free flight is really easy on heat, short runs then a long wait. The larger motors and any overpowered ones will need ventilation, however. It's easy to solder wires onto motors, but we do this for you on the Dual Mini 6 and Mini 6 because it's harder to get to the tabs. The first step in the soldering process is to remove a very short section of the insulation from both wires. Apply flux to the ends of the wires and then tin them with solder. Always remember when soldering to any motor, short time is best. 1 second heat application is always the best. Tab mounts are thermoplastic insulators and will melt from the heat, distorting brushes and ruining the motors. Remove all flux with a solvent to prevent future corrosion at the joint. We are now going to build up this assembly so you can see us actually make these connections. A commercially available third-hand fixture can be a big help with this job. The switch and jack should be mounted for convenience on the bottom usually. We supply a plate for smaller motors, but if you really wish, you can separate them for better scale effects. This is the trickiest part to solder. It's very easy to melt the parts in either the switch or the jack. Now follow along with us as we solder one of these assemblies for you. Soldering battery tabs uses exactly the same technique. Larger components are used with our larger motors to be able to handle the greater current. They are more easily soldered because they are larger. No plate is included for these. Mount them on a sheet for recessing. Also note that larger wires are used for the larger motors. 18 American wire gauge versus 22 gauge. This is necessary to handle more current without current loss. Heavier wire than this is not necessary. Never solder inside the airframe. The risk of damage is too high. Solder wires onto all major component lumps, leaving extra wire. Wire is cheap and doesn't add much weight. Then mount the components. Last, connect the wires by pulling them out the frame, twisting them together, and soldering. Stuff them back in. When you mount the switch with CYA glue, for some reason the stuff sucks right into the switch, immobilizing it. There's no saving it, so be careful when the cement goes on. Use gap-filling CYA and cure it quickly with a kicker. The battery pack is the largest mass in the airplane. This is unusual for the first-time electric flyer. It seems like you're putting an anvil in the airplane, but trust me, it will all work out. In the design section, I mentioned making the battery pack movable. Do this only when setting up your components. After that, the last thing you want is a loose battery banging around inside the airplane. Talk about a loose cannon. Allow some extra wire length. Move the pack to optimum balance, then carefully mount it to the airframe. My favorite method is to build a small box of styrofoam encapsulating the cells. Fasten the cells to the foam with RC56, which is tough and flexible. CYA can be bad in impact situations. The foam should be of a size and shape to fit snugly inside the fuse, touching the inside members as many places as possible. Glue the foam to the frame with RC56 or white glue. Well, here we are at the batteries and charging section. Now, isn't that an intimidating looking pile of stuff? I must confess that it was intimidating to me. I'm a model builder. I'm not a battery expert. But the point is, I don't think you have to be a battery expert in order to fly electric-powered model airplanes. We can all do it. We'll just use them the best we can. I arrived at my usage of them by trial and error, mainly. So don't let that scare you off. We use Sanyo batteries. Sanyos are from pagers and cell phones and various other appliances to which we are indebted so that we have a good source of these little guys. And they're extremely reliable and a lot of current for their weight. Let's take a look at each of the battery systems individually. Batteries are rarely used singly because we need more voltage than that to run our motors. They are made up in packs, the smaller ones with solder tabs, the larger ones with wires, and a thin wrap of heat shrink material to keep them together in a tough insulated bundle. Batteries are connected in series, plus to minus, which makes the voltage add in 1.2 volt increments. 2 cells puts out 2.4 volts. 3 cells, 3.6 volts. 4 cells, 4.8 volts, and so on. In actual use, with a motor drawing on it, the battery will drop down to about 2 volts for 2 cells and 3 for 3 cells. So a good rule of thumb is to think you get about 1 volt for each cell in a battery pack. Highline takes a lot of the figuring out of this by recommending the most commonly used battery packs for each motor. Only get into worrying about batteries if there is a problem. All motors have a safety factor on voltage and amperage for long life. Many modelers will play around in this safety range to get more performance. Fine if you know what you're doing, but some of our motors, like the ducted fans, are already at the top of the safety range, and there is no margin left. Ask us, we can tell you these. This is the Micro 4 motor, which runs on 2 or 3 cells. The Mini 6 power system will run best on 3 or 4 cells. A dual Mini 6 motor runs most happily on 3 or 4 cells also. An IMP30 runs on the widest range of cells, from 2 through 4. The Troll 35, which is the same size as the IMP30 but more modern, derives slightly more power because it will handle more cells, 4 or 5. The Highline L50 and the geared Gnome 50 are primarily for RC flying and will run on 4 or 5 cells for the ELF or 6 or 7 for the Gnome. Of course, the cells are larger for longer duration. The Blue Flame Blaster has the Troll 35 mounted in it, so it also runs on 4 or 5 cells. The Red Flame Blaster has the L50 mounted in it, and we use 5 or 6 cells by combining various smaller packs to fit inside a jet-type fuselage. Length of time the motor will run depends on how big the battery pack is. Cells are rated in mAh, or milliamp hours, which is electric jargon for the ability to produce current over time. First, convert the number on the cell by multiplying by 60 and dividing by 1,000. A 100 mAh cell reduces to 6 amp minutes, which means this battery pack will deliver 1 amp for 6 minutes before exhaustion. 200 milliamp hours will last for 12 minutes at 1 amp, and so on. You may write this on your flight box for all the cells you use as a quick reference. So now you have a quick way to tell how much is in a battery. But how much does your motor draw when it is running? We'll show you that a bit later, or we give it to you in the catalog, as most manufacturers do. Say your motor draws 2 amps on the prop you have chosen. The above battery would deliver 1 amp for 6 minutes, so it would put out twice that for half the time, or 2 amps for 3 minutes. Get the idea? These are all ideal values and can vary slightly in actual use. The best thing to do is to put a precise charge in the battery and run your motor system, measuring run time. This is particularly critical if you will be flying a free flight model where a mistake can mean a lost model. One last thing to remember is that the propeller unloads in the air. Static thrust puts more load on a battery, therefore it won't last as long. Flying your model takes less effort and you will get a longer run from a charge. You can lose a model from this effect, so go cautiously until you know your power system well. I promised you that I'd show you how to measure the current draw with a particular prop and motor combination. Here is the hookup with a meter in the circuit with the motor. This meter is a digital voltmeter purchased from Radio Shack. Be sure you get one that will handle 10 amps current. The settings are as follows. First, plug the leads into the 10 amp connection points. Set the lower knob to DC amps and the upper knob to the 30 range. I am using a large battery from this charger, so the reading will stay more constant than with a smaller battery. We complete the circuit and throw the switch to on. The current is displayed digitally in the window. This schematic is also shown in the manual that comes with the meter. Now that we've talked about batteries and how to calculate their run times and such, let's think a moment about charging. There are a number of ways to put current into a battery. Let's start with the simplest ones. One of the most direct is to take flashlight batteries. You can get a holder like this, pop in 3 flashlight batteries, and it's got a connector on it that'll plug right into your charging system in the airplane. And for as long as the batteries last, you'll have a usable charging system. In fact, we sell these as our entry-level charging circuit. That just plugs right into the airplane and gives you all you would possibly need. But you will get tired of buying batteries. They don't last that long. So the next step up would be to get some batteries that are rechargeable. So we put together a little kit of multiple NiCads, large size ones, in a pack with the same jack plug onto it. And you can charge these up, and these will run for a whole weekend of hard charging and hard flying, to be used just like the flashlight batteries were. They're a little expensive because the NiCads are more expensive than flashlight batteries, of course. This is not the kit we make. The one we make is a little more streamlined like that, and you have a choice of 2 different output levels. This is particularly nice as a charger if you're test flying, because you can put it in your pocket, leaving the wire out of your pocket, and just walk about the field charging and flying and charging and flying. So that's particularly nice from that standpoint. But if you fly near your car, we sell one that will do just about the same thing, only uses your car cigarette lighter as a connection point. This is probably the most versatile one, and it has a knob on it that allows you to select the different sizes of amperages that you want to charge at, and cells. On one side you have a 1 amp charge rate, on the other side you have a 2 amp charge rate. The bigger packs you'd want to charge at 2, and the smaller ones you'd want to charge at 1. Then we have the number of cells also clicked on there. So if you want to charge 2 cells at 1 amp, you set that on there, plug it in, the light goes out when it's charged. Very nice because you can run from 2 to 6 cells with this little charger, and it's probably less expensive than buying even the NiCads would be. If you are going to use anything other than these for competition, you'll run into the problem that they are blind, in that I don't know exactly how many amps are going into the airplane, and I don't know exactly for how long. What you need is a charger of a little more sophistication. We're moving up the scale now, such as this charger, which has a time and current adjustment. I plug it into the car, and this one also has a nice feature in that you can plug it into your house as well as plugging it into your car. And you set the time on a timer, say 5 minutes, and the timer begins, and you adjust the current, which will read out on an ammeter. So now if I'm competition flying and I want to hit a 2-minute flight time, I know exactly what amps to set and how much time, and I can repeat that perfectly every time. This is also very good for larger packs and more different sizes of cells than the smaller ones. But this is not a blind charger. This gives you that exactitude that you need. Now, if you're an RC flyer, you're more concerned with the fact that you want to fly as long as you possibly can. An RC charger, therefore, puts a peak charge in. We don't use peak chargers because we rarely peak out a battery. You would get a surefire flyaway if you peak charged your airplane. So you want a controlled amount of charge. So these kind are more advantageous for what we are doing. Consider the case where you're test flying. In other words, I've got a brand new airplane and I want to put 10 seconds of charge on there to see whether it's going to do a headstand and dive into the ground. So I'll quick put a tentative charge in there, fly it a little bit, and then gradually increase the length of charge until the plane is flying safely while I adjust it. You can't do that with a peak charger. There are extremely sophisticated chargers which will do lots of things. You can program stuff into them and all. The best way to do that is go to your hobby shop and have someone demonstrate it for you. Lots of folks make chargers. So this is one where we're playing at the low end of the scale and to the person that's just getting going. Perhaps I should say a little more about peak charging. The RC world is going to be interested in this. This charger does have 2 connections where you could put a voltmeter on it and read out the point at which the cells charge up fully. The way you tell this is the voltage begins running up, and you watch the point at which it stops increasing and begins to drop ever so slightly, and at that point you turn it off. That is your charged peak. That's a way of, again, filling the cells as far as they will go, right up to the top. You're not caring about a formula or anything, you're just filling them right to the top. Okay, I have here a timed style charger, which we spoke about earlier, wherein I can set the time in minutes, I can set the current to what I wish and read the whole business out on a meter. That gives me the most control of the charge I'm putting in the airplane. So we first plug the thing into the cigar lighter. And we're ready to charge. I'll go through a practice trimming session. This is a little set of batteries in this one, so I'll only charge it for a short time at a low amperage setting. We'll charge it for a minute. Charging at a 1.5 amp rate. That's as low as my rheostat will go on that. We're approaching the end of our 1 minute charge time, so I'm going to just advance it till it stops, which ceases the charging. Pull out the jack, and we're ready to fly. Pretty easy, huh? Make one last minute check of alignment, then it's a case of just throw the switch and toss the plane. First step in flying is always turn your switch completely off. That makes the connection between the charger and the battery. If you're still in the on position, it will not charge, and you have wasted the time just sitting there doing nothing. It only charges in the off position. Now I'm going to charge at a 2 amp rate for this battery. Because it has a larger number of cells. Once again, this is the Calibri in action, an airplane which is about 10 years old for me, but still in excellent flying shape. Electrics don't get dirty, as we mentioned before. I've now just put a 1 minute charge in there, because I don't want it to fly off the field in this light breeze. Notice that you have a freewheeling cam on this motor, so you must make sure that the motor is pulled out, the prop is pulled out so that the motor is engaged, so that when your motor starts, it will not strip the gears. This is the Dornier Delphin 3, made about the late 20s in Germany and used in Switzerland. We have a dual Mini 6 in this with 4 200 batteries. Once again, switch off, and then you can begin charging. This charging system allows me to put in exactly what I want and not risk losing the airplane. I can set exactly what I think is a timed amount of current and not put it out of sight. This field is not unbelievably large. Your flight schedule when you build a brand new airplane should be to put a very short charge in and fly the plane for 10 seconds. See what's happening, make any corrections to the flying surfaces you have to, ballast it if needed, and fly it again and keep raising the charge time 10 seconds each time until you're up around a minute. Then you're flying safely and the plane is not likely to change when you give it more power. The electric is nice that way. When you give it full charge, it doesn't run any differently than when you give it a light charge. At least these size airplanes don't. So that you can gradually work your way up through the trimming exercise, making all your adjustments by just short little bursts of flights. Behind my back. Pull the cam out. So that's 1.5 minutes charge. Notice that the motor has quite a torque effect. This is a very large airplane for this size motor, and yet it still turns extremely strongly to the left from torque. Okay, as we said before, the timed charger allows you to calculate exactly how long you want it to fly and put in just the right amount for the field conditions. This is a very valuable thing in a charger. Make sure if you're buying a charger that you can do that with it. It's going to spin in the beginning or doesn't. A neat little trick is to write on and off on your switch plate. That helps immeasurably when you go to leave the thing. Also, I always write the number of cells and the amperage because I fly so many different airplanes. I tend to lose track of how long to charge them. So that way I make less mistakes and ruin less batteries. Once again, I'm charging at a rate of 1.5 amps. We'll put this one up for about 1 minute. Here goes. Ooh, bad launch. We covered anyway. Now that we've gotten back from that wonderful flying session, I promised you a State of the Union talk about RC and these motors. If you are contemplating flying electric RC airplanes this size, you first have to think micro everything. You can't use anything larger than the absolute lightest stuff available. Servos that size, half an ounce. Speed controls. Do everything you can to keep the weight to an absolute minimum. I try and stay 2 ounces, maybe 2.5 ounces, because you just carry the weight into that never land where the plane doesn't fly as well. We'd love them to fly at about 1 pound, but it will take up maybe 18, 19 ounces. This one is 19 ounces. So you've still got to work with very lightweight gear and do a lot to keep the weight down. I would recommend a BEC system. BEC stands for Battery Eliminator Circuit. That's where the battery for the motor and the battery for the radio are the same. They share that power source. You say, well, if that's the case, what happens when the motor uses up the power? How do you've lost your radio. But that's what a BEC does for you. It cuts out the motor, the drive system, while there is some residual power still in the batteries, enough to supposedly bring you back to the field in a gliding situation. It has the nice advantage that you only have to charge one system up so that your receiver is always charged. If the motor runs, it's got power to also run the receiver. Unfortunately, not all the BECs are available in this light, small size. They're beginning to become available like that. So you may end up with an auxiliary pack to run the receiver. That's what we have in here. I have a speed control that does not have a BEC in it. And I used the smallest pack I could get. It's a little 4 by 50 milliamp hour pack. And the whole thing weighs just a shade over 2 ounces for a 3-channel rig. As of right now, the radio is being flown regularly only using our larger motors. Remember the larger round motors, the 02 and the 035 size? That's where the bulk of the radio use is right now. Bill Cannon of Cannon Radio Systems is manufacturing a very nice little tiny light one. And I think with care and weight control, you can then fly the biggest of our geared small motors. We're still not down there into the tiny ones yet in anything but an experimental setup. However, we feel that this is going to be coming very shortly. A number of manufacturers have let it be known that they are working on very lightweight equipment. Particularly the outfits in Germany and in other parts of Europe. So I would expect it will be not long before we're flying RC with our smallest motors, possibly within a year. I know that there are flyers right now flying indoor RC. I have no sight, so I haven't been able to join them in this effort. But just as soon as it stabilizes and the equipment becomes readily available on a basis which I can, handle, we will jump right into that market. I think it's going to be the next big wave. So be sure and watch out for developments in this area. Before we leave this section, I should say a word or two about the structure used in the airplanes. If you come from the RC world, your building style will be too heavy. The liberal use of sheet wood, solid members, and heavy plastic coverings are just too much for this size airplane. We don't have that kind of power available. So this plane is built more like a competition rubber model was built. Not a lightweight scale rubber model, but one of the large endurance rubber models. It's built up of a single tube backbone, which is the jet tube. The formers are slid onto that, and then stringers are put on as a skin, covered again with light span from England. This makes an extremely lightweight structure and will ease the load on that poor little power plant trying to pull a plane this size. And one last thing, resist the temptation to load up on the batteries to get more power. All you'll do is just increase the weight to the point where it won't fly right. A light model is always more fun to fly. So try and aim for a pound or a little bit more, and you should be most happy with the performance of these kinds of planes. This is the part where I would tell you about advanced projects. This is really the interesting part of it. The electric power systems lend themselves perfectly to multi-engine subjects. We can now do things that no other power system can do. This is the nether end of the B-36. Unfortunately, the other end of it is laid up in the shop for repairs temporarily. You can still see it on the photographs, however, and what it did at the Nationals last year. But whoever heard of six motors, running like that in perfect harmony, perfectly naturally. Remember, they all start together and they all run with exactly the same power because they come off the same battery source. The old way of flying the planes was to use props turning the exact same direction. And to take care of torque, which would then be pretty phenomenal, you tilt the right motor down slightly and the left motor up slightly. You can't see it because it's so slight. It's only a couple of degrees, but that gave you a roll moment to the right, which compensates for the roll moment to the left from the motors. Kind of tricky, but we've now recently come up with matched propellers in opposite hands. In other words, the props turn in opposing directions. That's easy to do with electric because you just reverse the wires on one motor, and they therefore run as a opposition. You can see they go opposite directions. This takes all the torque out of it, and the plane now has less torque problems than a single-motored airplane would. There is some question as to which way to run them. As soon as you have opposing motors, you get the question of, do you want them to come together at the top or apart at the top? It depends on the configuration. I tried both ways on this airplane till I finally settled on one that worked. What you get is some kind of a backwash effect that affects the stab, and it'll look nose light one way and nose heavy the other way. So all I can suggest is experiment with your particular twin if you're going to be doing a twin. There is another problem associated with multiple installations which you should be aware of, and that's the problem of whether to connect motors in series or parallel. I can give you some advice on that, but you can understand that the possibilities are limitless here. The smaller motors are easily run in parallel because they don't draw that much current to begin with. A parallel circuit can easily be hooked up with most battery systems. As you start to get more motors or bigger motors, suppose you were running some of our larger sized motors which draw a fair amount of current, a parallel circuit would draw more power than most batteries can deliver. They would just cook. So you have to mount them in series just for that reason. The B36, we experimented both ways, and the lightest battery system and the best power came out with series parallel. In other words, I mounted opposing pairs, this pair and this pair and this pair, in series, and then hooked those three in parallel, making sort of a homogeneous mixture by the time it got to the batteries. So a lot of experimenting goes on. But certainly the sky is the limit now on multi-motor subjects, and don't let any configuration, no matter how outlandish, stop you. The electric can do it. Well, we've had quite a nice time together. I've gone through all the constructional and flying things I can possibly add. So we've hoped you've enjoyed the lecture, and we've answered most of your questions. If you have further questions, we have a number on the front of our catalog where we can be reached. You can write us, and we'll be glad to talk further with you. And send us a picture of your planes. We're always collecting more ideas and becoming sort of a clearinghouse for electric data. Until then, let's fly electric.